Compound curves are a special type of horizontal curve that feature two horizontal curves that are placed back to back. The place where those two curves adjoin is known as the point of compound curvature. And we're going to take a look at a real example at an interchange loop where a compound curve is commonly used. This is at the interchange of I-40 and Aviation Parkway, and we're specifically going to look at quadrant C and the loop in quadrant C. So this is what the design plan looks like. Zooming into this loop, we can see some additional detail, and we'll walk through each of the major components of this compound curve and this loop system that connects Aviation Parkway to I-40, or essentially an arterial or a cross street to an access control facility at this interchange. So isolating just the loop here, and in the upper left we see the curve details for the three curves that make up loop C. So I'm going to start by just talking through the important stations on this loop, and then we'll come back and talk more details about the curve elements themselves. So pointing out here with these red circles, we're going to start with station 10, and this is where we tie in to the interstate. We're going to work back up the loop to station 12. Then most of the way around the loop now we get to the PCC, the point of compound curvature, which is station 17 plus 44.35. And our last station for the loop is station 20 plus 6.66. So those are the important stations on this loop. Now let's talk about what we actually have located there. So we have a simple curve with these details that are summarized in the curve table, and that's the portion here in red. Then the next curve is again another simple curve, and that's the second part of our compound curve. And again, where those two meet, so we've got the green portion there, which is the second part of the compound curve. Where they meet is the point of compound curvature, the PCC. And then we end with a spiral transition to the interstate with those given characteristics. In terms of the stationing, again, summarizing what's going on, we had station 10, and that's the start of that spiral transition to the interstate. Station 12, which is the end of the spiral transition, and we were given that length of spiral of 200 feet. And we can do the math between station 10 and station 12, that's 200 feet, and that's our spiral transition. Then we have station 17 plus 44.35. Again, that's the PCC. And that's the end of the simple curve that had a length of 544.35 feet and a radius of 200 feet. So that's our larger radius curve. And then we end with station 20 plus 06.66. And that's the end of the simple curve with a length of 262.32 feet and a radius of 150 feet. So summarizing that, station 10 is the start of the spiral, station 12 is the end of the spiral. Then we go to our first simple curve that ends at station 17 plus 44.35. And then our final station is station 20 plus 06.66, which is the end of our loop as it connects back to our arterial or cross street at this interchange. Let's take a little closer look at the stationing. So we talked about that station 10 was the start of the station for the loop. The first simple curve has a PI of station 21 plus 38.65. They were given that in the curve table, and we show it here with the simple curve that's in green. And the second curve has a PI station of 19 plus 23.74. So how is that possible? The first curve you encounter as we're moving along and moving up in stationing, the first curve has a PI station that is larger than the second simple curve. So let's take a look at why that happens. So we had to shrink the loop here so we can make sure we can show the points of intersection, because those fall very far off of this loop. So we start with station 12, and that's where we leave our spiral transition and enter that larger radius. So we have a tangent that connects from that point. to the end of the curve. So this is where our beginning of the first curve and starts, and the end of the first curve ends. Those connect at station 21 plus 38.65. And we can see the point to connect those tangents is pretty far away from that loop. And again, this is the first curve that you encounter in terms of increasing stationing. We're given a tangent length of 938.65, and that helps us go back and establish the start of this curve. The red portion is the actual curve itself, so that's the length for this part of the compound curve, 544.35 feet. That first curve ends at the PCC, which has a station of 17 plus 44.35. And then we have our tangent for our second part of the curve. The tangent length is 179.39 feet. And those tangents intersect at the point of intersection, which is station 19 plus 23.74. We've got our length there, the red portion that finishes out our compound curve system. Remember, for a compound curve, we've got two curves that are adjoining that have different radius values. And that ends at station 20 plus 06.66. So summarizing what we see in the stationing example and why we had our first curve has a larger station value than our second curve. We had this sharp curve as part of the loop with a radius of 200 feet, and it's comparatively long given the sharpness of the curve, has a length of 544.35 feet. That pushes the point of intersection far away from the curve, and therefore the PI for the curve has a larger station than the following curve. Thinking a little bit big picture about curvature, so we have that spiral transition to the interstate. We've got our simple curve with a 200-foot radius, and we've got a simple curve with a 100-foot radius. And as we would like to have, the larger radius is closer to the higher speed road, and this allows drivers to gain speed as they transition to merge onto the interstate through that spiral transition at the end. So if we've got a vehicle, it starts with a smaller radius and then ends up on the larger radius and the spiral transition to help it accelerate and merge onto traffic on the interstate.